Hello everyone. Today we are going to look at the first part of chapter 10, which is all about work and the work energy theorem. So our learning targets today are to be able to define the word work and to examine the relationship between work and energy. And our questions that we're going to try and answer: what is work? How are energy and work related? All right, so let's jump right in. So we're going to start with review, almost like we almost always do. What is energy? So this should be familiar to you now. Energy is the ability to change the environment. And remember, by environment, we don't necessarily mean like the beach or the forest or something like that, right? Anything is a change to an environment. If you walk forward, if you pick something up, if you drop something, all of those things are the change in the environment. We have focused on two types of energy. So we have focused on potential energy, which remember is energy that's stored, and mostly we're using gravitational potential energy. So when you lift something, so our formula that we have been using is potential energy equals mgh. This, of course, is in joules. Kinetic energy is the other form of energy that we've been focusing on, and kinetic energy, remember, is the energy of movement. Anything that's moving has kinetic energy. And the formula we've been using here is kinetic energy is 1/2 mv squared, and of course it's also in joules. All right, and then we're going to think way back to first semester, because for work we also need to know a force, and the force we're going to focus on is weight. So how do you find weight? Well, weight is the force of gravity pulling on a mass. And remember that the way we find the weight of something is we say Fg equals m times g. And g, of course, is 9.8 as long as you're on the Earth. All of our problems today are going to be on the Earth. We measure force in newtons. That's supposed to look like an N. Let me try again. There we go, in newtons. All right, so all those things should sound familiar to you. Take a minute and think about them if you need to. So, our first essential question: what is work? So work is one of those terms, right, that you hear all the time. Your parents say, I'm going to work, or you're going to work out, or you're going to work hard, or maybe you have homework, or maybe you have yard work or housework. Work in physics class is a very specifically defined concept, and work is using a force to move an object through a distance. Okay, so here's the important stuff here is using a force. Oh, I didn't even finish that word. Wow. Let's try that again then, shall we? A force. Okay, so using a force to move an object through a distance. The formula that we are going to use for this, W stands for work, is equal to F is force, D is distance. Pretty straightforward, huh? So work equals force times distance. And because work and energy are so closely related, we are also going to measure this in joules. So just like energy, work is measured in joules. All right? Now, there are some important conditions here that we have to think about, okay? So in order for work to be done, there has to be a force, there has to be a distance, and the trick here is that they have to be in the same direction. So in this particular example, the person with the box is exerting a force in this upward direction, right? Because the person is holding the box. but the person is moving forward. So that's my distance. So because those two things are not in the same direction, this person is not doing any work. Now that's a little bit tricky because depending on how heavy the box is, his arms might be getting tired, or how far he's walked, his legs might be getting tired. But he's not doing any work in a sense of physics because the force and the distance are in two different directions. So let's go ahead and put that over here. Important conditions for work to occur. First of all, there must be a force. Second of all, the object must move. So in other words, if you were pushing as hard as you could push, exerting as much force as you could on like the wall of your house, right? You wouldn't be doing any work because the object wouldn't be moving. Your house wouldn't be going anywhere. All right, and lastly, the force and the distance must be in the same direction. That's not what I meant to do. This is what I meant to do. They must be in the same direction. Otherwise, there's no work that happens. All right, let's see how good you are at this. So this is your turn. For each of these little pictures, I want you to decide, yes, there is work being done, or no, there's not work being done, and you need to tell me why. So let's do this first one together. So here's my force going up, here's my distance or displacement going forward. There is no work being done here because force and distance in different directions. Okay, so that's what I want you to think about it. You can stop the video, please, and do the second and third pictures here and tell me yes or no, is there work being done? Make sure you say why. All right, so let's go ahead and take a look at an example problem here, and we'll see how we use this formula. So it says you are climbing a cliff with 1.2 kilogram water bottle attached to your waist. If you climb 9.7 meters in 25 minutes, how much work did you do on the water bottle? All right, so let's take a look at our picture first. Here's the water bottle. I am exerting a force up because I'm climbing. I'm carrying the water bottle, so the water bottle is moving through a distance going up. So is there work? Yes, there's work being done here. Okay. So now let's see if we can figure out how much. So it tells me that I have a mass of 1.2 kilograms. It tells me that I have climbed a height of 9.7 meters. And it tells me it took me 25 minutes to do this. And I'd like to know how much work I did. So if we want to find work, we're going to have to do force times distance. Unfortunately, I don't have a force right now, but I do have a mass, and I can use the mass to find the force and then use the force to find the work. So this is going to be a two-part problem. So part one, we have to find the force. And in order to do that, we are going to find the weight of the water bottle. So mg. So I'm going to have Fg equals 1.2, that's my mass, times 9.8 because I am climbing this cliff on the earth. And my force is going to be 11.76 newtons. Okay, so now that I know the force, I can find the work. Work is force times distance. So the work is going to be 11.76 times 9.7 meters. That's how high I climbed. And the work is going to be 114 joules as my final answer. So notice I didn't use the time. Do we care about the time? Do I want to know how fast I climbed this cliff? No, I really don't. I just need to know how much force I used and how far I went. All right, so your turn. A dog picks up a 1.5 kilogram newspaper off the ground, 0.35 meters, and carries it into the house. Calculate the amount of work done by the dog. So turn the video off. Go ahead and give that a shot. All right. Now remember, if you have any questions about this, make sure that you write them down in your notes so that you remember to ask in class. All right, so far we've talked about work and the conditions of work. So now we are going to look at question number 2 here. How are work and energy related? Okay, and so this brings us to something called the work-energy theorem. And the work-energy theorem gives us the relationship between work and energy. That makes sense, right? So the work-energy theorem tells me that work is equal to a change in energy. As a matter of fact, sometimes when we define energy, we say it's the ability to do work. Okay? And work is the change in energy. So we can say for this theorem that work is equal to the change in potential energy, or we could say that work is equal to the change in kinetic energy. Either one of those things. Also other kinds of energy, but we're focusing on potential and kinetic. So let's go ahead and see how this kind of all works out. That was a pun. I didn't even mean it to be. Okay. An Olympian does a clean and jerk, that's lifting the weights right over your head, with 45 kilograms to a height of 2.2 meters. Calculate the change in energy of the weights. Okay, so what do we know? We know the mass of these weights is 45 kilograms. We know that the height it got lifted to is 2.2 meters. We know that we're on the Earth, so we can put acceleration due to gravity in there if we need it. And we are looking for the change in potential energy. Everybody good? Okay. So remember that change in potential energy means the final potential energy minus the starting potential energy, or initial potential energy. And so if I fill this stuff in, I'm going to have the change of potential energy is equal to mg final height minus mg initial height. Right? Mass isn't going to change, acceleration due to gravity isn't going to change, but the height, that's going to change. So if I keep going, I can fill in the change in potential energy is 45, right? That's the mass, times 9.8, and 2.2 meters off the ground is where we ended up. Minus 45, that's still the mass, 9.8, that's still acceleration due to gravity, but these weights started on the ground, so my initial height was 0. So if I go ahead and do my math, I'm going to come up with the change in potential energy is equal to 40, let me get my calculator, 45 times 9.8 times 2.2 is going to be 970 minus 45 times 9.8 times 0 is 0. So my change in potential energy is 970 joules. Okay, so that's part A, change in energy. Calculate the work done by the athlete. Okay, so I know that work is force times distance, but I also know that work is equal to the change in potential energy. And since I just figured out the change in potential energy is 970 joules, I know that the work is also 970 joules without doing any calculation because that's the change in potential energy. Isn't it nice that they're measured in the same units? That is one reason they're measured in the same units, right? Joules and joules and joules. Work is equal to the change in potential energy. Work is equal to the change in kinetic energy, and they are all measured in joules. All right, so your turn. A bobsled team have a mass of 325 kilograms. They start at rest. They are moving at 45 meters per second at the end of the bobsled run. Calculate the change in kinetic energy. Calculate the work done. So that first one, part A, that's going to require you to do some actual math. That second one, though, you should be able to do just like the one we did up above, because remember that the work is equal to the change in kinetic energy. All right, as always, write down any questions that you might have so we can talk about them in class, and I will see you next time. Thank you so much.